Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey into the cosmos, take a moment to get comfortable wherever you are. Let your body settle into this space. Where in the world are you watching from? A quiet bedroom as the day finally releases you? A cozy corner where night has already fallen? Perhaps you're somewhere between waking and dreaming, seeking that gentle passage into sleep. Tonight we're going to explore 5 profound mysteries that continue to puzzle astronomers, cosmologists and physicists across the world. We'll discover what dark matter might be and why we can't find it, understand the strange signals coming from deep space that defy easy explanation, and contemplate the nature of black holes that seem to break the rules we thought governed reality. It's a journey that spans the observable universe and reaches back to the first moments after creation itself. These aren't horror stories from space, they're invitations to wonder. But don't worry, this isn't going to be a breathless race through alarming revelations meant to keep you on edge. Instead, we'll move slowly and carefully through each mystery, taking our time with the evidence, the theories, and the brilliant minds trying to solve these cosmic puzzles. By the end, I think you'll find there's a profound peace in accepting that the universe still holds secrets, that there are still frontiers of understanding waiting to be explored. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these journeys into the night sky. So settle in now, let your shoulders drop away from your ears, take a slow breath in and let it out even more slowly. And let's begin our slow drift through the mysteries that wait in the darkness between stars. There's nowhere you need to be right now. Nothing you need to solve or fix or understand completely. Just listen and let the story of the universe unfold around you like the night itself. Let's begin with something that sounds impossible. Everything you can see, everything that has ever been observed through any telescope, every star and planet and nebula, every galaxy spinning in the cosmic dark, all of it together makes up less than 5% of what the universe actually contains. The rest is something we've never directly detected. We call it dark matter, and it's one of the most profound mysteries in all of science. The story begins in the 1930s with an astronomer named Fritz Zwicky studying galaxy clusters through telescopes in California. Zwicky was measuring how fast galaxies were moving within these clusters, expecting the numbers to match up with the visible mass he could observe. But they didn't match. The galaxies were moving far too quickly. At those speeds, the clusters should have torn themselves apart long ago, galaxies flung out into space like water from a spinning sprinkler. Yet the clusters remained stable, held together by something Zwicky couldn't see. He proposed something radical. There must be matter there, he said. Matter that doesn't emit light or absorb it. Matter that exists only through its gravitational influence on the things we can see. He called it dark matter, and for decades most astronomers dismissed the idea. It seemed too convenient, too much like inventing an invisible substance to explain what you didn't understand. But the evidence kept accumulating, quietly insistent. In the 1970s, astronomer Vera Rubin studied how spiral galaxies rotate, measuring the speeds of stars at different distances from galactic centers. The stars at the outer edges were moving just as fast as those closer in, sometimes even faster. This violated everything we understood about orbital mechanics. Stars farther out should move more slowly, just as outer planets in our solar system take longer to complete their orbits. Call a dark matter halo. This halo call a dark matter halo. This halo contains perhaps 5 or 6 times more mass than all the visible stars, gas and dust combined. It's like discovering that the house you live in is actually just a small room inside a much larger mansion you never knew existed. And this brings us to something equally remarkable. The question of what this invisible substance actually is. If dark matter makes up roughly 27% of the universe, you might think we'd have found it by now. Scientists have been looking for decades, building increasingly sophisticated detectors deep underground, sending instruments into space, analysing data from particle colliders. Yet dark matter remains stubbornly invisible, defined more by what it isn't than what it is. We know dark matter doesn't interact with light. It doesn't emit radiation, doesn't absorb it, doesn't reflect it. Light passes through dark matter as if it isn't there at all. This is why we can't see it with telescopes, no matter how powerful. We also know dark matter doesn't interact with normal matter through any of the fundamental forces except gravity. It doesn't participate in the electromagnetic force, which means it can't form atoms or molecules. It doesn't seem to feel the strong nuclear force that binds atomic nuclei together. The leading theory suggests dark matter consists of particles that have never been directly observed. Physicists have given them names like WIMPs, which stands for weakly interacting massive particles, theoretical particles that would have mass but interact with ordinary matter only through gravity and possibly through the weak nuclear force. If WIMPs exist, they should occasionally collide with the nuclei of normal atoms, producing tiny flashes of energy that sensitive detectors might catch. Experiments like the Large Hadron Collider have searched for evidence of these particles in the debris of high-energy collisions. Deep underground, in former mining facilities converted into laboratories, tanks filled with liquid xenon or germanium crystals wait in perfect darkness, shielded from cosmic rays, watching for the telltale recoil of a nucleus struck by a passing dark matter particle. So far, these experiments have found nothing conclusive, though they've successfully ruled out many theoretical possibilities. There are alternative theories, each with its own elegance and problems. Perhaps dark matter consists of axions, hypothetical particles far lighter than electrons, existing in such vast numbers that their collective mass shapes the cosmos. Or maybe dark matter is actually primordial black holes, formed in the first fraction of a second after the Big Bang, too small to be directly observed but numerous enough to account for the missing mass. Some physicists have even questioned whether dark matter exists at all, proposing instead that our understanding of gravity breaks down at galactic scales, that the equations describing how gravity works might need modification. These theories, called modified Newtonian dynamics or MOND, have had some success explaining galactic rotation curves, but they struggle to account for other observations that dark matter explains quite naturally. The truth is, we're searching for something we've never seen, using instruments designed to detect particles we're not certain exist, guided by theories that may or may not correspond to reality. It's a kind of cosmic detective work where we know something happened. We can see its effects everywhere, but the culprit remains invisible, leaving only gravitational fingerprints behind. Which leads us naturally to consider where else these fingerprints appear, written across the largest structures in the universe. If you could see dark matter, if there were some way to make it visible to human eyes, the universe would look profoundly different than the emptiness we imagine when we think of space. Instead of isolated galaxies scattered through darkness, you'd see an immense web-like structure, filaments of dark matter stretching across hundreds of millions of light years, connecting galaxy clusters like beads on cosmic strings. Astronomers call this the cosmic web, and it's the largest known structure in the universe. The filaments are vast rivers of dark matter flowing through space, with galaxies forming along them like cities along ancient trade routes. Between these filaments lie enormous voids, regions where almost no galaxies exist, empty spaces that can span 300 million light-years or more. The universe, at its largest scale, looks something like foam, like the structure you'd see in a kitchen sponge magnified to cosmic proportions. This structure didn't form randomly. Computer simulations that include dark matter can reproduce the cosmic web we observe with remarkable accuracy. These simulations begin with the early universe, just after the Big Bang, when matter was distributed almost uniformly with only tiny density variations. Dark matter, being more abundant and not interacting with radiation like normal matter does, began collapsing under its own gravity first, creating gravitational wells that normal matter then fell into. Over billions of years, dark matter formed the scaffolding upon which visible structures assembled. Galaxies didn't form in isolation and then drift together. They formed where dark matter was already concentrated, in the densest parts of the cosmic web. The Milky Way, our home galaxy, sits within one of these dark matter halos, embedded in a filament that connects us to the Virgo supercluster, a concentration of thousands of galaxies about 50 million light-years away. What's fascinating is that we can map this invisible structure by observing its effects on light. When light from distant galaxies passes through regions of concentrated dark matter, the gravitational field bends the light's path, a phenomenon called gravitational lensing. By studying how background galaxies appear distorted or magnified, astronomers can create maps of where dark matter must be concentrated. Seeing its shadow cast across the cosmos, these maps reveal dark matter's distribution isn't uniform within galaxies either. Our own galaxy's dark matter halo extends perhaps 600,000 light-years from the galactic centre, far beyond the visible disk of stars which spans only about 100,000 light-years. We're living inside this halo right now, dark matter particles streaming through the Earth, through your body, through everything, every second of every day, leaving no trace we can detect. The thought is both humbling and strange. An invisible ocean surrounds us, shapes the motions of stars, determines where galaxies form and how they evolve, yet remains completely imperceptible to our senses and most of our instruments. And this connects to something equally important. The realization that what we can see is merely a luminous trace of a much larger hidden reality. In 2006, astronomers studying a massive galaxy cluster about 3.7 billion light-years away found what many consider the most compelling evidence yet for dark matter's existence. The Bullet Cluster, as it's now called, is actually two galaxy clusters that collided with each other roughly 150 million years ago, passing through each other at speeds of several million miles per hour. When clusters collide, their galaxies mostly pass by each other like ghosts. Stars are so far apart that actual stellar collisions are extraordinarily rare. But the hot gas between galaxies, which makes up most of the normal matter in clusters, doesn't pass through so easily. This gas interacts electromagnetically, creating friction, heating up, slowing down. In the Bullet Cluster, X-ray observations reveal this hot gas concentrated in the middle, between the two clusters, shock-heated to tens of millions of degrees by the collision. But here's what makes this observation remarkable. When astronomers used gravitational lensing to map where most of the mass in the system was located, they found it wasn't in the middle with the hot gas. Most of the mass had passed straight through the collision, continuing with the galaxies themselves, now separated from the gas by millions of light-years. The mass was in two distinct concentrations, one with each cluster of galaxies, exactly where you'd expect dark matter halos to be if dark matter doesn't interact with normal matter except through gravity. This separation of visible matter from gravitational mass is difficult to explain without dark matter. The galaxies and their associated dark matter halos pass through each other largely unaffected, while the normal matter that could interact electromagnetically got left behind in the collision zone. It's like watching two swarms of fireflies pass through each other in the night, the insects continuing on their paths while the light they emit somehow stays suspended in the middle. The Bullet Cluster isn't unique. Astronomers have since found similar systems, galaxy clusters caught in the act of collision, showing the same pattern of separated normal and dark matter. Each one provides another piece of evidence that something invisible and massive exists, something that feels gravity but little else, something that makes up the majority of matter in the universe. Yet even with this evidence, dark matter remains hypothetical in the sense that we've never directly detected a dark matter particle, never captured one in an experiment, never studied its properties in a laboratory. We've inferred its existence from gravitational effects. mapped its distribution across cosmic scales, included it in our models of how the universe evolved, but we've never held it in our hands, so to speak, never examined it directly. This situation would frustrate some. But there's a beauty in it too. The universe is telling us clearly that our understanding is incomplete, that there are fundamental constituents of reality we haven't discovered yet. The mystery invites continued exploration, better experiments, new theories, creative thinking about the nature of matter and gravity. Let that thought settle as we move forward into our second mystery, something even stranger than invisible matter, signals from deep space that shouldn't exist. On August 15th, 2001, a radio telescope in Australia detected a burst of radio waves lasting just 5 milliseconds. The signal was incredibly bright, releasing as much energy in those 5,000ths of a second as the sun produces in an entire day, yet it came from somewhere beyond our galaxy, billions of light years away. No one noticed it at the time. The burst was discovered 6 years later by a graduate student named David Narkovich, who was analysing archival data looking for pulsars and found instead this strange, powerful, brief flash from the depths of space. They called it the Lorimer Burst, after Duncan Lorimer, the astronomer supervising the research. For years it remained an isolated curiosity, one weird data point that might have been a glitch, an error, interference from Earth-based sources. But then more bursts were found in other archival data, and radio telescopes specifically designed to look for these events began detecting them regularly. They're now called fast radio bursts, or FRBs, and they represent one of the most perplexing phenomena in modern astronomy. Fast radio bursts share certain characteristics. They're incredibly bright, visible across billions of light years despite lasting mere milliseconds. They arrive at Earth with their radio frequencies slightly spread out in time, lower frequencies arriving a bit later than higher ones, a signature of having travelled through ionized gas across cosmic distances. This dispersion allows astronomers to estimate how far away the burst originated, and the distances are staggering, typically billions of light years, placing their sources in distant galaxies. What makes these bursts so mysterious is the sheer amount of energy released so quickly. To produce that much radio emission in milliseconds requires extreme conditions, temperatures, or magnetic fields far beyond anything we normally encounter. The bursts also show structure within their brief existence, multiple sub-pulses separated by milliseconds, suggesting whatever produces them is small, probably no larger than a few hundred kilometres across. Something small, distant, and extraordinarily energetic is producing these signals. Most fast radio bursts appear just once and never repeat, coming from random directions in the sky without warning, making them nearly impossible to study in detail. You can't point a telescope at a source before it happens, can't watch it evolve over time, can't predict where the next one will appear. It's like trying to study lightning by seeing only individual flashes reflected in puddles, never knowing which puddle will light up next. But a small percentage of fast radio bursts do repeat, flashing again and again from the same location in space, sometimes dozens or even hundreds of times. These repeaters have allowed much more detailed study. Astronomers have pinpointed some to specific galaxies, have measured precise distances, have analysed the polarisation and structure of the radio waves. One particularly active repeater, catalogued as FRB 2021-02A, produces bursts on an almost regular schedule, becoming active for a few days then quiet for a few weeks in a predictable cycle. The source of fast radio bursts remains uncertain. The leading theory points to magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, perhaps the most powerful magnetic fields in the universe. When these magnetic fields reorganize themselves, like how the sun's magnetic field creates solar flares, they might produce the intense radio emission we detect as fast radio bursts. In 2020, astronomers detected an FRB coming from a magnetar in our own galaxy. the first time a source could be definitively identified, lending support to this theory. But not all FRBs fit the Magnetar model easily. Some show characteristics that are difficult to explain with current theories, polarization patterns that suggest the radio waves pass through extraordinarily strong magnetic fields, brightness variations that hint at some kind of orbital motion or precession. And this is where our journey takes an interesting turn, leading us to consider what other explanations might exist and what these mysterious signals might tell us about extreme physics operating at the edge of what's possible. To understand why magnetars might produce fast radio bursts, we need to understand what magnetars are, and that requires contemplating one of the most extreme objects in the universe, the neutron star. Imagine taking the entire mass of our Sun, about 2 times 10 to the power of 30 kilograms, and compressing it into a sphere just 20 kilometers across, roughly the size of a city. The matter becomes so dense that a teaspoon of it would weigh about 1 billion tons on Earth. This is a neutron star. Neutron stars form when massive stars exhaust their nuclear fuel and collapse. The outer layers explode as a supernova while the core implodes, crushing matter to densities where protons and electrons merge into neutrons. What remains is essentially a giant atomic nucleus, nuclear matter held together not by chemical bonds, but by gravity fighting against neutron degeneracy pressure. The surface gravity is about 200 billion times stronger than Earth's. Light itself is noticeably bent by the intense gravitational field. But some neutron stars form with something extra, magnetic fields of unimaginable strength. These are magnetars. The magnetic field strength can reach 10 to the power of 15 Gauss, about 1,000 trillion times stronger than Earth's magnetic field, strong enough that the quantum vacuum itself becomes affected, polarizing space in ways that alter how light propagates. If a magnetar existed where the moon orbits, its magnetic field would be lethal to humans on Earth, would erase every magnetic storage device on the planet, would pull the iron from your blood. These fields aren't stable. They evolve, twist, and occasionally reorganize themselves catastrophically in events called magnetar flares or starquakes. The neutron star's crust, solid nuclear matter, about 1 kilometer thick, cracks under the stress of the shifting magnetic field. The field lines reconnect violently, releasing enormous amounts of energy in seconds or milliseconds, energy that gets channeled into electromagnetic radiation, including radio waves. In December of 2004, a magnetar called SGR 1806-20 produced the largest burst of energy ever recorded from a source beyond our solar system. For 1/10 of a second, this object, located about 50,000 light-years away, was brighter in gamma rays than anything in the sky except the sun. The radiation was so intense it measurably affected Earth's upper atmosphere, ionizing part of the ionosphere. This was from an object the size of a city, halfway across the galaxy. When astronomers detected a fast radio burst from a known magnetar in the Milky Way in 2020, it seemed to confirm that magnetars could produce these signals. The burst matched the characteristics of extragalactic FRBs, but was much closer, allowing detailed study. It showed the same millisecond duration, the same brightness relative to distance, the same frequency structure. The case seemed solved, yet mysteries remain. The galactic magnetar produced only one FRB-like burst before falling silent again, while some extragalactic sources repeat thousands of times. Some FRBs show frequency patterns and polarization signatures that don't match magnetar models perfectly. Perhaps there are multiple types of sources, different mechanisms producing similar-looking bursts. Perhaps magnetars produce FRBS only under specific conditions we don't fully understand yet. Building on this foundation, we can now explore what else might generate these mysterious signals, and whether some of them might have truly exotic origins. Science progresses through the interplay of evidence and imagination, observation and theory. While magnetars provide a plausible explanation for many fast radio bursts, the universe has often surprised us by being stranger than our initial theories suggested. It's worth contemplating what else might produce these powerful millisecond radio flashes. One alternative involves merging neutron stars or black holes. When two compact objects orbit each other, they lose energy through gravitational waves, spiralling ever closer until they merge in a catastrophic collision. In the final moments before merger, the intense gravitational forces and magnetic fields might produce brief, powerful radio bursts. We know such mergers occur because gravitational wave detectors have observed them, and at least one merger produced electromagnetic signals including radio waves. The timing could work. The final moments before merger last milliseconds, matching FRB durations. The energy available in the collision is certainly sufficient, and mergers would be one-time events, explaining why most FRBs don't repeat. But there are problems with this theory too. Mergers should produce distinctive gravitational wave signatures that we could detect for nearby events, yet no FRB has been conclusively associated with a gravitational wave detection. The merger rate doesn't quite match the observed FRB rate, and the fine details of the radio emission don't perfectly align with merger predictions. Another possibility involves supramassive neutron stars, objects balanced on the knife edge between being a neutron star and collapsing into a black hole. These would be the most massive neutron stars possible, spinning rapidly to support their weight against collapse. Such objects might be unstable, prone to sudden changes in rotation or magnetic field configuration that could produce radio bursts. Eventually they would collapse into black holes, which might explain why some FRB sources seem to turn off permanently after a final burst. There are even more exotic proposals. Some astronomers have speculated about cosmic strings, hypothetical defects in space-time left over from the Big Bang, vibrating and producing electromagnetic radiation when disturbed. Others have suggested primordial black holes evaporating through Hawking radiation, though this seems unlikely to produce the observed signals. Each theory must explain not just the brightness and duration of FRBs, but also their rate of occurrence, their distribution across the sky, their tendency to repeat or not repeat, and the detailed structure of their radio emission. What's fascinating is how these theories can be tested. As telescopes become more sensitive and can locate FRB sources more precisely, astronomers can study the galaxies hosting these events, looking for clues about what kinds of environments produce them. Are they in old galaxies with aged stellar populations? Or young galaxies forming stars rapidly? Are they associated with supernova remnants or regions of intense star formation? Are they more common in certain types of galaxies or at certain cosmic epochs? The answers emerging suggest diversity. Some FRBs come from active star-forming galaxies where you'd expect young magnetars to exist. Others come from older, quieter galaxies where magnetar formation should be rare. This diversity might mean multiple types of sources exist, or it might mean magnetars can form through pathways we haven't fully understood, perhaps through the merger of white dwarfs or the collapse of massive white dwarfs in old stellar populations. There's also the question of what happens to the radio waves on their journey across billions of light years. They pass through intergalactic space, through the ionized gas in galaxy clusters, through the outskirts of galaxies, each region leaving its mark on the signal. By analysing how FRB signals are affected, astronomers can learn about the intervening material, essentially using fast radio bursts as probes of the universe's structure. And this connects to something equally important, the realisation that these mysterious signals might become tools for understanding cosmic evolution, and the distribution of matter we can't easily observe any other way. Radio astronomy might seem less romantic than optical astronomy, with its stunning images of colourful nebulae and spiral galaxies. But radio telescopes reveal a universe invisible to our eyes, a cosmos filled with energetic phenomena that don't shine in visible light. Fast radio bursts are just one example of this hidden universe making itself known. The radio telescopes searching for FRBs are engineering marvels. Facilities like CHIME in Canada, the Canadian Hydrogen Intensity Mapping Experiment, consist of 4 cylindrical reflectors, each 100 metres long and 20 metres wide, stationary on the ground, monitoring half the sky above them continuously. As Earth rotates, different parts of the sky pass through their field of view, and sophisticated signal processing systems analyse the incoming radio waves in real time. Searching for the characteristic signature of an FRB among the cosmic noise and Earth-based interference. CHIME detects several fast radio bursts every day, far more than earlier telescopes found in years of searching. This abundance has transformed FRB studies from examining rare curiosities to conducting statistical analysis of a large population. Astronomers can now ask questions about typical properties, about variations and outliers. In Puerto Rico, before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. In Puerto Rico, before its collapse in 2010. The Arecibo telescope in Puerto Rico, before its collapse in 2020, provided unmatched sensitivity. The Very Large Array in New Mexico could locate FRB sources with high precision when it caught one. Australian telescopes like ASCAP, the Australian Square Kilometre Array Pathfinder, combine wide fields of view with the ability to determine which direction a burst came from, allowing immediate follow-up observations. Together, these facilities have catalogued thousands of FRBs, building a dataset that reveals patterns in what initially seemed random. One pattern involves the relationship between an FRB's dispersion and its distance. Dispersion measures how much the radio signal spreads out during its journey, with lower frequencies delayed relative to higher frequencies by interaction with free electrons along the path. The more electrons encountered, the greater the dispersion. Since electrons are distributed throughout space, greater dispersion generally means greater distance. This relationship allows astronomers to estimate distances to FRB sources even without identifying the host galaxy. But there are complications. Electrons aren't uniformly distributed. They cluster in galaxies, in intergalactic gas, in the halos of galaxy clusters. Some FRBs show excess dispersion that must come from material in or near the source itself, perhaps a supernova remnant or a pulsar wind nebula surrounding a young magnetar. Untangling these contributions requires careful analysis, comparison with independent distance measurements when possible, and statistical methods applied to large populations of bursts. The bursts themselves show intriguing variety. Some are single smooth pulses, others consist of multiple subpulses, complex structure, playing out in milliseconds that might encode information about the emission mechanism or the environment near the source. A few bursts show downward drifting frequency structure, the emission starting at high frequencies and progressing to lower ones. A pattern seen in some pulsar emissions and thought to relate to the geometry of rotating magnetic fields. Then there's the question of polarization. Light and radio waves are electromagnetic waves that can be polarized, with the electric field oscillating in a specific direction. Some FRBs show very high levels of circular or linear polarization, implying the radio waves passed through or were generated in regions with extremely strong magnetic fields. The Faraday rotation, a change in polarization angle that depends on magnetic fields and electron density along the propagation path, can reveal the magnetic field strength in the source environment or in intervening space. All of this data, thousands of bursts with measured properties, is building toward a comprehensive understanding of what fast radio bursts are and what produces them. The picture emerging is complex. probably involving multiple types of sources or different physical conditions producing different varieties of bursts from similar types of objects. There's a kind of peace in accepting this complexity, in understanding that the universe doesn't always fit into simple categories, that mysteries can have layered answers requiring patience to unravel. Let's rest here for a moment with this thought before moving deeper into even stranger territory, where the universe's most extreme objects bend reality itself. Our third great cosmic mystery takes us to places where space and time themselves become strange, where gravity grows so intense that not even light can escape, where our best theories of physics predict their own failure. We're talking about black holes, objects so dense that they create tears in the fabric of space-time, and specifically about what happens at their centres, at points called singularities, where matter is crushed to infinite density, and the laws of physics as we understand them simply stop working. Black holes aren't hypothetical anymore. In 2019, astronomers released the first image of a black hole's shadow, a dark circle surrounded by glowing hot gas, captured by linking radio telescopes across the entire Earth into a planet-sized instrument. In 2020, the Nobel Prize in Physics went partly for the discovery of a supermassive black hole at the centre of our galaxy. We've detected gravitational waves from merging black holes, observed stars orbiting around invisible companions, mapped X-ray emissions from matter spiralling into these cosmic drains. Black holes are real, confirmed by multiple lines of evidence, yet they remain deeply mysterious. The mystery begins at the event horizon, the boundary beyond which nothing can escape. Despite its name, the event horizon isn't a physical surface. It's more like a one-way membrane in space-time, a point of no return. Cross it moving inward, and every possible future path leads further inward toward the centre. Time and space exchange roles in a sense. Just as you inevitably move forward in time outside a black hole, you inevitably move inward in space once you've crossed the event horizon. Escape becomes as impossible as travelling backward in time. But what exists at the centre? General relativity, Einstein's theory of gravity, predicts a singularity, a point where matter is compressed to infinite density, where the curvature of space-time becomes infinite, where the mathematics produces infinities that signal the theory's breakdown. Physicists generally interpret infinities in physical theories as signs that something is wrong with the theory at that scale, that we're missing some crucial piece of physics that would resolve the infinity into something finite and comprehensible. For large black holes, this evaporation is extraordinarily slow. A black hole the mass of the Sun would take longer than the current age of the universe to evaporate completely. But smaller black holes evaporate faster, and in the final moments, they should release enormous amounts of energy in a burst of radiation and particles. No one has ever observed a black hole evaporate, but the theory is well established, and most physicists believe it's correct. Hawking radiation creates what's called the black hole information paradox. According to quantum mechanics, information cannot be destroyed. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time. But if information falls into a black hole, and the black hole then evaporates completely via Hawking radiation, which appears to be random thermal radiation, with no information content, then the information seems to have been destroyed. This contradiction suggests either quantum mechanics or general relativity must be modified, or we must understand something new about how information escapes from black holes. Recent theoretical work suggests information might be preserved through subtle correlations in the Hawking radiation, or through a breakdown of the event horizon's smoothness at quantum scales, but the paradox remains unresolved in any complete, proven way. Which leads us naturally to consider what other puzzles black holes present, and whether understanding them might require an entirely new theory of physics that unifies quantum mechanics and gravity. The deepest mystery surrounding black holes is that they exist at the intersection of two great theories of physics that don't fit together. General relativity describes gravity as the curvature of space-time caused by mass and energy, and it works brilliantly at large scales. Planets, stars, galaxies, the expanding universe. Quantum mechanics describes the behaviour of matter and energy at atomic and subatomic scales, and it too works brilliantly, explaining chemistry, electronics, nuclear physics, the behaviour of light. Yet the two theories are fundamentally incompatible. General relativity is deterministic and continuous, space-time a smooth fabric that can be bent and curved but remains a continuum. Quantum mechanics is probabilistic and discrete, with particles existing in superpositions of states until measured, with energy coming in discrete packets called quanta. When you try to apply quantum mechanics to gravity, or general relativity to quantum scales, the mathematics produces nonsensical results, infinities and contradictions that can't be resolved within the frameworks of either theory. This incompatibility doesn't matter for most situations. Gravity is by far the weakest fundamental force, negligible at atomic scales where quantum mechanics reigns, and quantum effects are negligible at the scales where gravity matters, like the orbits of planets or the expansion of the universe. There's a vast middle ground where both theories' predictions are so small they can be ignored, allowing physicists to use whichever theory is appropriate for the scale they're studying. But at black hole singularities, both theories must apply simultaneously. Gravity becomes infinitely strong at the singularity, requiring general relativity, yet the singularity is infinitely small, a quantum-scale object, requiring quantum mechanics. The two theories give different, contradictory answers about what happens there, and we have no way to resolve the contradiction. A complete theory of quantum gravity, one that successfully merges the two frameworks, would tell us what actually exists at black hole centres. String theory is one attempt at such a unification. It proposes that fundamental particles aren't point-like, but tiny vibrating strings of energy, existing in 10 or 11 dimensions, with most dimensions curled up so small we can't observe them. Different vibration patterns of these strings correspond to different particles: electrons, quarks, photons, and also gravitons, hypothetical particles that carry the gravitational force. String theory naturally includes gravity as one of the fundamental forces alongside electromagnetism and the nuclear forces, offering a potential framework for quantum gravity. But string theory remains unproven and perhaps untestable with current technology. It makes few definite predictions that we can check with experiments or observations. Other approaches to quantum gravity exist. Loop quantum gravity, which proposes space-time itself, is discrete rather than continuous at the smallest scales. Causal dynamical triangulations. Asymptotically safe gravity. Each has mathematical appeal and faces practical challenges in making testable predictions. What these theories might tell us about black hole interiors remains speculative. Loop quantum gravity, for instance, suggests singularities might be replaced by high-density but finite regions where matter bounces back out, creating what's called a white hole on the other side. String theory offers possibilities involving black holes being related to other objects called fuzzballs, tangled configurations of strings that have no true singularity inside. Without experimental or observational tests, we can't know which, if any, of these ideas correspond to reality. There's something both frustrating and exhilarating about reaching the limits of our understanding this way. We've identified precisely where our knowledge breaks down. We have theories that work in their respective domains, we know they're incomplete, and we have smart people working on extensions and alternatives. The mystery isn't unsolvable in principle, it's just unsolved for now, waiting for a breakthrough in theory or observation or both, waiting for the next Einstein to see what everyone else has missed. And this, in turn, leads us to contemplate the nature of time itself near black holes, where clocks slow down and eternity unfolds differently depending on where you stand. Let's slow down here and consider something that seems simple: time. We experience it as a constant flow, seconds ticking by at an unchanging rate, the future becoming the present, becoming the past in steady progression. But near black holes, time behaves in ways that challenge this intuitive understanding, stretching and slowing until, at the event horizon itself, time from an outside perspective seems to stop altogether. This isn't science fiction or speculation. It's a confirmed prediction of general relativity, tested and verified through multiple observations. Time runs slower in stronger gravitational fields, a phenomenon called gravitational time dilation. The effect is tiny in everyday circumstances. Clocks at sea level run very slightly slower than clocks on mountaintops because they're deeper in Earth's gravitational field. But the difference is real and measurable with precise atomic clocks. Near a black hole, this effect becomes dramatic. Imagine watching someone fall toward a black hole's event horizon. As they approach, you'd see them slow down, their motion becoming more and more sluggish. Light from them would shift toward red, becoming dimmer and dimmer. They would appear to freeze, forever suspended at the event horizon, never quite crossing it, gradually fading from view as the light becomes too red-shifted and dim to detect. But from the perspective of the person falling in, nothing strange happens at the event horizon. They cross it in finite time by their own clock, feeling no special sensation at the boundary. It's only when they approach the singularity that tidal forces, the difference in gravitational pull between their head and feet, become strong enough to notice and eventually to tear them apart in a process gruesomely called spaghettification. This divergence between perspectives reveals something profound about the nature of time and space. They're not absolute, not the same for everyone, but relative, depending on your motion and your position in gravitational fields. Two observers can disagree about how much time has passed or whether events happen simultaneously, and both can be right from their own reference frames. For a supermassive black hole, like the one at the centre of our galaxy, which contains about 4 million times the Sun's mass, the event horizon is large enough, and the gravitational gradient gentle enough that a person could cross it without immediately being torn apart by tidal forces. They might survive for hours or even days before approaching the singularity, experiencing that time normally from their perspective. Yet to an outside observer who watched them fall in, those hours would stretch to eternity. They would never see the infalling person actually cross the horizon or reach the singularity. This raises deep questions about what it means for something to happen. If we can never see matter actually cross the event horizon, does it happen? From a practical observational standpoint, matter piles up at the horizon, getting ever more compressed and red-shifted but never disappearing. From the perspective of someone with the matter, crossing happens normally. Both views are valid in their reference frames. Black holes also create closed time-like curves in certain solutions of Einstein's equations, paths through space-time that loop back on themselves, theoretically allowing time travel to one's own past. These solutions, particularly in rotating black holes, are probably not physical, excluded by additional principles or instabilities, but they exist mathematically, showing how flexible and strange the concept of time becomes in extreme gravity. The interplay between time and gravity has practical implications too. GPS satellites must account for both the weaker gravity they experience in orbit, which makes their clocks run slightly faster, and their motion relative to the ground, which makes their clocks run slightly slower due to special relativity's time dilation. If these effects weren't corrected for, GPS positions would drift by kilometers per day. We navigate using technology that works only because we understand how time flows differently in different gravitational fields and states of motion. But to fully appreciate how strange time becomes, we need to explore what happens when we try to combine our understanding of time with quantum mechanics, where particles can be in superpositions of states, and where observation affects reality in fundamental ways. Hold on to that image as we continue into territory where the questions become even more philosophical. One of quantum mechanics' most counterintuitive features is that observation affects what is observed. not just in the sense of disturbing a delicate system, but fundamentally changing the nature of what exists. Before measurement, a quantum particle doesn't have definite properties, but exists in a superposition of all possible states. The act of measurement forces it to choose, to collapse into one specific state, and different types of measurements can yield different, incompatible information. Consider the famous double-slit experiment. Fire electrons one at a time through two narrow slits toward a detector screen. The electrons arrive one by one, individual particles making individual dots on the screen. But over time, the pattern that builds up is not what you'd expect for particles. Instead of two bands corresponding to the two slits, you see an interference pattern, alternating bright and dark bands, the signature of waves interfering with each other constructively and destructively. Each electron somehow went through both slits simultaneously, interfered with itself, then arrived at a specific point on the screen. If you try to determine which slit an electron actually went through by placing a detector at the slits, the interference pattern disappears and you get the two-band pattern you'd expect for particles. The measurement changes the outcome, not because it physically disturbs the electron, but because it fundamentally alters what kind of entity the electron is, forcing it to be a particle rather than a wave. This isn't a limitation of our instruments or knowledge, it's how quantum systems actually behave. A particle genuinely doesn't have a definite position until measured, exists instead as a spread-out wave function, describing probabilities of finding it different places. When you measure position, you collapse that wave function, but now momentum becomes completely uncertain in a complementary way. Measure momentum precisely instead, and position becomes uncertain. You can't know both precisely at the same time, not because you can't measure well enough, but because they don't both have definite values simultaneously. The implications for black holes are subtle but profound. If you drop something into a black hole, does its quantum information fall into the singularity and get destroyed, or does it somehow remain encoded on the event horizon, accessible in principle to outside observers? A hologram encoding three-dimensional information in a two-dimensional surface. For black holes, this would mean all the information that falls in remains encoded on the event horizon itself. There's also the question of what happens during black hole evaporation. As a black hole loses mass through Hawking radiation, it shrinks. The event horizon gets smaller, the temperature of the Hawking radiation increases, and eventually the black hole evaporates completely in a final burst of energy. But Hawking radiation appears to be thermal, random, carrying no information about what fell into the black hole. So where did the information go? Stephen Hawking initially believed information was truly destroyed in black hole evaporation, a process that would violate quantum mechanics' fundamental principle that information is conserved. Later in his life, he changed his view, proposing that information might escape through subtle correlations in the Hawking radiation that we don't fully understand yet. The question remains unresolved, touching on the deepest issues in theoretical physics. Some theories propose that what we perceive as a black hole with an interior is actually all surface from a fundamental perspective. The event horizon containing all the information in a form that appears three-dimensional to us, but is actually encoded two-dimensionally in ways we don't yet fully grasp. Others suggest the interior might not exist at all as we imagine it, that the singularity and inner structure are effective descriptions that break down when quantum effects are properly included. The role of observation and information in quantum mechanics raises philosophical questions that physics alone might not answer. Does a quantum system's wave function represent something physically real, or is it just a mathematical tool for calculating probabilities? When we say a particle is in a superposition of states, does it actually exist in multiple states simultaneously? Or do we just lack complete information about which state it's in? Does measurement reveal a pre-existing reality, or does it create reality through the act of observation? Different interpretations of quantum mechanics answer these questions differently. and no experiment has definitively ruled out any major interpretation. The Copenhagen interpretation treats wave function collapse as fundamental, but doesn't explain what causes it. The many worlds interpretation says the wave function never collapses, but the universe splits into multiple branches at each measurement. Pilot wave theory proposes particles always have definite positions guided by an underlying wave. Each interpretation makes the same experimental predictions, but offers different pictures of underlying reality. This uncertainty about interpretation extends to black holes. What really exists at the centre? What happens to information that falls in? Is the interior real or an effective description? These questions sit at the boundary between physics and philosophy, where empirical science reaches its limits and we must confront how much we can truly know about reality's fundamental nature. And so we find ourselves at the threshold of our fourth mystery, one that involves not individual objects but the structure of the entire universe, the expansion of space itself, and the dark energy driving it to accelerate. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that shocked the physics community. They expected to measure how much the universe's expansion was slowing down due to gravity pulling everything together. Instead, they found the expansion is speeding up. The universe isn't just expanding, it's accelerating, driven by something we now call dark energy, and that discovery earned the Nobel Prize in Physics in 2011. The evidence came from Type 1 supernovae, exploding stars that make excellent cosmic distance markers. These supernovae happen when a white dwarf star accumulates too much mass from a companion star and crosses a critical threshold, igniting carbon and oxygen fusion that tears the white dwarf apart in a thermonuclear explosion. Because this threshold mass is always the same, about 1.4 times the Sun's mass, these supernovae always have the same intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance. The research teams looked at supernovae in distant galaxies billions of light years away, comparing their distances to their redshifts, how much the expansion of the universe has stretched their light toward redder wavelengths during its journey to us. The relationship between distance and redshift encodes the expansion history of the universe. If expansion were slowing down, distant supernovae would be closer than expected for their redshift. If expansion were constant, they'd match a simple linear relationship. But the distant supernovae were farther away than expected, too dim for their redshift, implying expansion was slower in the past than it is now. Something is pushing space apart, counteracting gravity, and this something has grown stronger over time. About 5 or 6 billion years ago, the universe's expansion transitioned from decelerating to accelerating. Since then, acceleration has been increasing, and all evidence suggests it will continue forever. We call this mysterious force dark energy, but that name is more a label for our ignorance than an explanation. We don't know what dark energy is. We measure its effects on the expansion of space and its contribution to the universe's total energy density, about 68% of everything that exists, but we don't understand its nature or origin. This interpretation has a major problem though. When you try to calculate the cosmological constant's value from quantum field theory, considering the energy of quantum fluctuations in the vacuum, you get a number that's about 10 to the power of 120 times larger than what we observe. This discrepancy, called the cosmological constant problem, is perhaps the worst prediction in the history of physics. Something is either cancelling almost all of this vacuum energy, or our calculation is fundamentally wrong, or we're missing something essential about how quantum fields work in curved space-time. Alternative theories propose that dark energy isn't constant but changes over time, a dynamic field called quintessence that slowly evolves as the universe expands. Or maybe gravity itself behaves differently at cosmic scales than general relativity predicts, and what we interpret as dark energy is actually a modification to gravity's long-range behaviour. Each theory makes slightly different predictions about how acceleration changes over time, predictions that future observations of distant supernova, galaxy clustering, and the cosmic microwave background might be able to test. The implications of accelerating expansion are profound and somewhat melancholy. In the far future, as acceleration continues, distant galaxies will recede from us faster than light can travel through expanding space. Will remain visible. The rest of the will remain visible. The rest of the universe will fade from view, and future civilizations trillions of years hence might have no way to know the broader universe exists at all. This, in turn, leads us to contemplate the ultimate fate of everything, and whether the story of the cosmos has a final chapter or continues endlessly into an increasingly cold and dark eternity. With dark energy accelerating the universe's expansion, the cosmic future appears to be one of increasing isolation and entropy, a slow fade into cold darkness. But the details of how this unfolds depend on subtle properties of dark energy we haven't yet measured precisely, and the timeline stretches across timescales that make the current age of the universe seem like an opening moment. If dark energy remains constant or decreases slightly over time, the expansion continues forever, gradually cooling and diluting the universe. Stars will continue forming for perhaps another trillion years as hydrogen gas in galaxies collapses and ignites. But eventually the fuel runs out. The smallest, most economical stars, red dwarfs burning hydrogen so slowly they could shine for trillions of years, will be the last to go dark. After that, no more stars form. The universe enters the black dwarf era. Black dwarfs are the cold, dead remnants of stars like our sun, white dwarfs that have radiated away all their heat over tens of trillions of years, cooling to the temperature of the cosmic microwave background. Then even colder as the universe expands, and that background temperature drops toward absolute zero. These objects would be nearly invisible, emitting essentially no light, composed of crystallized carbon and oxygen, or possibly iron in white dwarfs massive enough to undergo slow fusion through quantum tunneling over immense timescales. Galaxies themselves slowly evaporate during this era. Stars randomly pass close to each other. And occasionally one gets enough velocity from such an encounter to escape the galaxy entirely, drifting off into intergalactic space. Over 10 to the power of 19 to 10 to the power of 20 years, roughly 1 billion times longer than the universe has currently existed, galaxies disperse. The remaining stars or stellar remnants fall toward the central black hole through a process called dynamical friction, getting absorbed over time. Black holes become the dominant structures, patient and cold, slowly evaporating through Hawking radiation. Small black holes evaporate relatively quickly, cosmically speaking, vanishing in trillions of years. But massive black holes like those at galaxy centers, containing millions or billions of solar masses, take far longer. A black hole the mass of the Sun would take about 10 to the power of 67 years to evaporate completely. Supermassive black holes at galaxy centers would take 10 to the power of 100 years or more. Timescales so vast they're almost incomprehensible. After the black holes evaporate, the universe contains only the most stable particles. Electrons, positrons, neutrinos, photons, all spread through ever-expanding space, their average separation growing steadily. Even these might not be stable on truly vast timescales. Some theories predict protons eventually decay with a half-life of perhaps 10 to the power of 35 years, far longer than we can directly measure, but not infinite. If protons decay, then even the black dwarfs and neutron stars that survived everything else would slowly disintegrate, their matter converting into radiation and lighter particles. But there's another possibility. If dark energy isn't constant but grows stronger over time, as some models called phantom energy suggest, then acceleration could increase without limit, eventually becoming strong enough to tear apart gravitationally bound structures. First galaxy clusters would be pulled apart, then galaxies themselves, then solar systems, then planets, eventually even atoms, as the expansion of space itself overcomes the electromagnetic forces holding molecules and atoms together. This scenario is called the Big Rip, and it would end the universe not in cold darkness, but in a final moment when space expands infinitely fast and everything is torn to pieces. Current observations suggest the Big Rip is unlikely, that dark energy is probably constant or very slowly changing, but we can't completely rule it out yet. Future measurements of distant supernovae and large-scale structure will constrain dark energy's properties more precisely, telling us which future awaits. There's something strangely peaceful about contemplating these far futures. The timescales are so immense that nothing we do or don't do will matter to them. The stars will burn out whether we're here to see it or not. Black holes will evaporate in darkness whether observed or unobserved. The universe will expand regardless of our understanding. There's a kind of liberation in accepting the cosmic perspective, in understanding we're brief patterns of complexity in a universe that tends towards simplicity and equilibrium. Let's settle into this idea a bit more before exploring our final mystery. One that questions whether our universe is all that exists or merely one bubble in an infinite cosmic foam. Everything we can observe, from the nearest stars to the most distant galaxies, exists within what's called our cosmic horizon, a spherical region centered on Earth whose radius is about 46 billion light-years. This isn't because the universe is only 46 billion light-years across. It's because light from farther away hasn't had enough time since the Big Bang to reach us yet. The universe could extend far beyond what we can see, perhaps infinitely far. But there's a deeper question, one that takes us beyond observation into the realm of theoretical speculation. Does only one universe exist, or are there many, perhaps infinitely many, each with different physical properties, different laws of physics, different values for fundamental constants? This idea, called the multiverse, exists in several distinct forms, each with different implications and different degrees of speculation. The simplest multiverse concept comes directly from cosmology. If space is infinite and matter was distributed fairly uniformly in the early universe as observations suggest, then every possible arrangement of matter must occur somewhere, just by random chance across infinite volume. There could be other regions of space, beyond our horizon, where galaxies form differently, where civilizations arose on planets very different from Earth, even exact copies of our observable universe if you go far enough. This level 1 multiverse, as cosmologist Max Tegmark calls it, is almost unavoidable if space is infinite and the early universe was uniform. It requires no new physics, just the recognition that infinite space contains infinite possibilities, each realized somewhere. But we could never observe or interact with these distant regions. They're forever beyond our horizon, causally disconnected from us by the expansion of space. The more speculative version involves eternal inflation, the idea that the rapid expansion called inflation that happened in the universe's first fraction of a second might still be happening in most of space, with our observable universe just a region where inflation stopped, a bubble in a much larger inflating space. Other bubbles would form elsewhere as inflation randomly stops in different regions, each becoming a separate universe with its own Big Bang, its own physics potentially, its own evolution. These bubble universes would be truly separate from ours, not just distant, but existing in different regions of a higher dimensional space, possibly with different laws of physics if the fields that determine physical laws settle into different states in different bubbles. One bubble might have stronger gravity, another might have different particle masses. Another might not have formed atoms at all because the fundamental forces balance differently. An even more radical multiverse idea comes from quantum mechanics' many worlds interpretation. Every quantum measurement that has multiple possible outcomes creates a branching of reality, the universe splitting into multiple copies, one for each outcome. You don't observe this splitting because each version of you sees only one outcome in their branch of reality. But all outcomes happen, each in its own branch, creating an ever-branching tree of parallel worlds. In this view, there are other versions of you, identical up to some quantum event that went differently, living out slightly different lives in parallel worlds you can never access or observe. The interpretation is elegant mathematically, avoiding the mysterious collapse of wave functions in other interpretations, but it comes at the cost of accepting that reality constantly multiplies into uncountably many copies. Finally, there's the mathematical multiverse, the most speculative of all, proposing that every mathematically consistent structure exists physically somewhere, that mathematics and physics are the same thing, and our universe is just one mathematical structure among all possible structures. This includes universes with different numbers of spatial dimensions, different types of particles, different logical structures underlying reality. The multiverse is controversial in physics precisely because it might be untestable. If we can never observe other universes, never get information from them, never test predictions about them, then is the multiverse idea even science, or has it crossed into metaphysics and philosophy? Some physicists embrace multiverse theories as natural consequences of our best models, inflation and quantum mechanics. Others reject them as unfalsifiable speculation dressed up as science. There's also the anthropic principle to consider. If many universes exist with different physics, we naturally find ourselves in one where the physics allows life to exist, because we couldn't exist in universes where physics didn't permit complex chemistry or stable stars. This could explain some of the apparently fine-tuned properties of our universe, like why the cosmological constant is small enough to allow galaxies to form but not zero, without requiring deeper explanation. But whether multiple universes exist or our universe is all there is, we face the same reality of being unable to see beyond certain horizons, unable to test certain ideas directly, dependent on mathematics and reasoning to extend our understanding beyond what we can observe. And this very limitation, this acknowledgement that some questions might be unanswerable with our current methods, leads us gently toward the final section of our journey, where we contemplate not just cosmic mysteries, but what it means to live with mystery, to accept that some questions remain open. Behind every cosmic mystery are human beings doing the patient work of science, spending careers on questions they might never see answered, building instruments that will outlast them, analysing data in cold offices under fluorescent lights far from the romantic image of astronomy. These are the people who transform mysteries from vague wonderings into precise questions that can be tested and refined. Consider Vera Rubin, whose careful measurements of galactic rotation curves provided some of the strongest early evidence for dark matter. She worked at a time when women in astronomy faced significant barriers, when major observatories didn't have women's restrooms because they assumed women wouldn't be using their telescopes. She persisted anyway, driven by curiosity about how galaxies spin, making observation after observation at night while raising 4 children, accumulating data that would force astronomy to accept the existence of something invisible shaping the cosmos. Or Fritz Zwicky, who proposed dark matter decades before anyone took it seriously, based on his studies of galaxy clusters in the 1930s. Zwicky was brilliant and difficult, making enemies with his abrasive personality, calling other astronomers spherical bastards, meaning they were bastards no matter which direction you looked at them from. But he was right about dark matter, right about the existence of neutron stars years before they were discovered, right about gravitational lensing long before it was confirmed. His insights were ahead of their time, and he spent much of his career marginalised because of his personality, even as his ideas proved correct. Stephen Hawking spent his career exploring black holes theoretically, discovering Hawking radiation through pure mathematical reasoning, never able to observe a black hole directly, confined to a wheelchair by ALS from his 20s onward, eventually losing even the ability to speak, communicating through a computer that selected words as he twitched his cheek muscle. Yet his mind ranged across the universe, contemplating the nature of space-time at singularities, writing both technical papers that advanced physics and popular books that brought cosmology to millions. Jocelyn Bell Burnell discovered pulsars as a graduate student in 1967, noticing a strange repeating signal in radio telescope data that others had dismissed as interference. She brought it to her advisor's attention, and together they confirmed it was coming from space, from a rapidly rotating neutron star, the first such object ever detected. The discovery earned a Nobel Prize in 1974, but it went to her male advisor and another astronomer, not to Bell Burnell, who had actually found the signal and done much of the analysis. She continued in astronomy anyway, later serving as president of the Royal Astronomical Society. Gracious about the Nobel snub while acknowledging the gender bias in how scientific credit was distributed. These stories matter because they remind us that science is a human endeavour, done by people with egos and biases, people who make mistakes and fight over credit, people who persist despite obstacles because curiosity drives them more strongly than comfort. The mysteries we've explored tonight exist as formal problems in physics, but they're also questions that captivated individual human minds, that inspired careers, that motivated people to spend cold nights at telescopes, or long days debugging code, or months deriving equations, all in service of understanding a tiny piece of how the universe works. The scientists searching for dark matter particles in underground laboratories are hoping to make a detection before they retire, before their funding runs out, before their careers end. They know the odds are uncertain, that they might spend decades looking and find nothing, that the particles might not exist in the form they're searching for, yet they continue, refining detectors, analysing data, eliminating false signals, narrowing the parameter space where dark matter might hide. The astronomers cataloguing fast radio bursts are building careers on a phenomenon discovered only 2 decades ago, working in a field so new that every observation teaches something, but so uncertain that we don't yet know what these bursts fundamentally are. They write papers, proposing models, testing predictions, arguing with colleagues about interpretations, slowly building toward understanding through the accumulation of data and the testing of ideas against observation. The theorists working on quantum gravity are doing physics that might never be experimentally testable in their lifetimes, developing mathematical frameworks that unify gravity and quantum mechanics at scales far smaller than any particle accelerator can probe. They proceed on faith that mathematics correctly describes reality. The elegant equations correspond to something true about the universe, that understanding the mathematical structure of physics brings us closer to understanding what actually exists. And perhaps this is what matters most about the human dimension of cosmic mysteries, the recognition that we are small, temporary, confined to a tiny rock orbiting an ordinary star, yet capable of understanding things vastly larger than ourselves, of detecting invisible matter-shaping galaxies, of discovering radiation from the Big Bang, of contemplating the nature of reality at black hole singularities. This capacity for understanding, for asking questions that reach beyond immediate survival and comfort, might be as remarkable as any of the mysteries we've explored. Human senses evolved to help us survive on Earth's surface, to see visible light, hear sounds in air, feel temperature and pressure. We can't naturally detect radio waves or X-rays, can't sense gravitational waves or neutrinos, can't see dark matter no matter how closely we look. Everything we know about the cosmic mysteries we've discussed comes through instruments that extend our senses, technology that makes the invisible visible, that translates the inaudible into data we can analyse. The radio telescopes that discovered fast radio bursts aren't like optical telescopes with lenses and mirrors. They're vast arrays of antennas, metal structures that convert radio waves into electrical signals that computers can process. Chime, in Canada, looks like 4 enormous half pipes lying on the ground, 100 metres long each, their surfaces covered in thousands of individual radio receivers. As Earth rotates, different parts of the sky pass through their field of view, and computers analyze the radio signals in real time. Searching for the brief burst pattern characteristic of an FRB among cosmic noise and human interference, the computational challenges are immense. CHIME generates terabytes of data every day, more information than you could read in a lifetime, and must process it in real time to detect bursts that last only milliseconds. The signal processing systems use techniques like beamforming, digitally steering the telescope's sensitivity to different parts of the sky without moving the physical structure, creating multiple simultaneous beams that can watch different directions at once. Dark matter detection experiments employ different technologies. The Large Hadron Collider smashes protons together at nearly the speed of light, recreating conditions similar to the early universe, looking for new particles in the debris. Underground dark matter detectors like Xenon 1T use tanks of ultra-pure liquid xenon, cooled to negative 100 degrees Celsius, waiting for the tiny flash of light or electrons that would signal a dark matter particle colliding with the xenon nucleus. These experiments must be extraordinarily sensitive and extraordinarily careful to exclude false signals. Cosmic rays from space constantly rain down on Earth's surface would produce false detections if the experiments weren't shielded. That's why dark matter detectors are built deep underground, beneath mountains or in old mines, where kilometers of rock filter out cosmic rays. The detectors themselves are constructed from carefully selected materials, chosen to have minimal radioactive contamination, surrounded by additional shielding, cooled to reduce thermal noise. Even with all these precautions, false signals occur. Random fluctuations that mimic what a real detection would look like. Scientists must understand every source of background noise. Every way the detector could produce a false positive must reach certainty levels of 5 sigma or better, meaning less than a 1 in 3.5 million chance the signal is random fluctuation. Before claiming a discovery, gravitational wave detectors like LIGO represent perhaps the most sensitive instruments ever built. They detect ripples in space-time itself by measuring how gravitational waves stretch and compress the distance between mirrors, separated by 4 kilometers, watching for changes smaller than the diameter of a proton. To achieve this sensitivity, the mirrors must be suspended in vacuum, isolated from ground vibrations. Measured with laser light whose wavelength is stabilized to extraordinary precision, LIGO's detectors are L-shaped, 2 perpendicular arms each 4 kilometers long, with laser light bouncing between mirrors at the ends. When a gravitational wave passes through, it stretches one arm while compressing the other, creating a tiny difference in the light travel time that the detector can measure. But this difference is incredibly small, about 1/10,000th the diameter of a proton for the strongest waves LIGO has detected from merging black holes billions of light-years away. The James Webb Space Telescope, launched in December 2021, extends our vision into infrared light that human eyes can't see, wavelengths where the universe's most distant galaxies appear because their light has been redshifted by cosmic expansion during its journey across billions of years. Webb's mirror is 6.5 meters across, made of 18 hexagonal segments that unfolded in space, coated with gold to reflect infrared light efficiently. Webb orbits the Sun at a special location called the L2 Lagrange point, about 1.5 million kilometers from Earth, where a sun shield the size of a tennis court keeps its instruments cold, below minus 200 degrees Celsius, necessary for detecting faint infrared light without being blinded by the telescope's own heat radiation. The images it sends back show galaxies as they appeared less than 1 billion years after the Big Bang, stars forming in pillars of gas and dust, exoplanet atmospheres with chemical compositions we can analyze. Each of these instruments required years or decades to design and build, billions of dollars in funding, international collaborations bringing together thousands of scientists and engineers. They represent humanity's collective effort to see farther, to detect fainter signals, to measure more precisely, to to push the boundaries of what's observable. And these technological marvels don't just answer questions, they raise new ones, reveal new mysteries, expand the frontier of the unknown even as they illuminate small pieces of it. Behind the observations and instruments lies mathematics, the language in which physical laws are written, the tool that lets us take scattered data points and extract deep truths about how nature works. The cosmic mysteries we've explored are ultimately mathematical mysteries, questions about what equations correctly describe dark matter's distribution, what fields produce fast radio bursts, what happens to space-time at black hole singularities, what form dark energy takes. Mathematics in physics serves two purposes. First, it's descriptive, providing precise language for phenomena we observe. When Vera Rubin measured how fast stars orbit in spiral galaxies, she recorded data, velocities as a function of distance from galactic centres. Mathematics let her plot these measurements, fit curves to them, compare them with predictions from Newton's and Einstein's theories of gravity applied to the visible matter distribution. Second, mathematics is predictive, telling us what we haven't yet observed based on what we have. Einstein's general relativity, published in 1915, predicted that massive objects curve space-time, that light should be bent by gravity, that gravitational waves should exist, that black holes were possible. These predictions came from solving Einstein's equations, not from observation, yet they all turned out to be correct when technology advanced enough to test them. The equations themselves can be beautiful, compact expressions of profound relationships. Einstein's field equations relating space-time curvature to energy and matter can be written in a few lines using the mathematics of tensors and differential geometry. Schrödinger's equation describing quantum mechanics is similarly concise, an equation you could fit on a coffee cup, yet it governs the behaviour of every atom, every chemical reaction, every quantum phenomenon. But beauty doesn't guarantee correctness. Physicists have proposed many beautiful theories that experiment disproved. The universe doesn't care about mathematical elegance, only about what actually happens. So there's always this interplay between theoretical development, creating mathematical models that might describe reality, and experimental test, checking whether those models actually work, whether their predictions match what we observe. Dark matter illustrates this process. We have observations, galactic rotation curves, and gravitational lensing and the cosmic web that tell us something with mass exists that we can't see. Theorists propose models, WIMPs or axions or primordial black holes, each with mathematical descriptions predicting how these objects would behave, how we might detect them, what signatures they'd leave in data. Experimentalists build instruments based on these predictions, search for the predicted signals so far without definitive success, feeding back to theory what's been ruled out, narrowing the space of possibilities. Fast radio bursts present a different challenge. We see the phenomena clearly, but lack a complete theoretical framework explaining them. Models exist. Magnetar flares or neutron star collisions or more exotic possibilities, each with mathematical descriptions that can be compared to observations. As data accumulates, as we measure more bursts with more detail, we can test whether these models match reality, whether they predict the right distribution of burst properties, the right relationship between burst characteristics and source environment. The mathematics of black holes becomes especially strange near singularities. Einstein's equations predict their own breakdown there. Producing infinities that signal the theory is incomplete. Quantum field theory and curved space-time, which combines some aspects of quantum mechanics with general relativity, produces its own infinities and contradictions. These mathematical problems point physicists toward the need for quantum gravity, a more complete theory that doesn't break down at singularities, but resolves the infinities into something finite and comprehensible. String theory represents one attempt at such a theory, replacing point-like particles with vibrating strings existing in 10 or 11 dimensions. The mathematics is extraordinarily complex, requiring advanced techniques from abstract algebra and differential geometry. But it naturally includes gravity and avoids some of the infinities that plague other quantum gravity approaches. Whether string theory correctly describes reality remains unknown, but the mathematics itself is beautiful and rich, offering insight even if the physical interpretation eventually proves incorrect. There's something profound about this relationship between mathematics and physics. The universe didn't have to be comprehensible through mathematics. We might have lived in a cosmos where no simple equations described natural phenomena, where every event was unique and unpredictable, where no patterns existed to discover. Instead, we find that nature follows mathematical laws, that the same equations work everywhere we look, that relationships discovered in laboratories on Earth apply to the interiors of stars and the expansion of the universe. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, suggests something deep about the structure of reality, though what exactly it suggests remains debatable. Does mathematics exist independently of physical reality, a platonic realm of perfect forms that our universe happens to embody? Or is mathematics a human invention, language we created that happens to map well onto natural patterns? Different philosophers and physicists give different answers. 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Different philosophers and physicists give different answers, and perhaps the question itself reaches beyond what science can definitively resolve. What we can say is that mathematics has proven indispensable for exploring cosmic mysteries, for turning vague questions into precise problems, for making predictions we can test, for seeing connections between apparently unrelated phenomena. The mysteries remain mysterious, but they're mathematical mysteries now, questions we can frame precisely, attack systematically, hopefully solve eventually through the combination of better theory, better observations, and better understanding of the mathematical structures underlying physical law. Not all questions can be answered, even in principle. Some cosmic mysteries might be fundamentally unsolvable, not because we lack clever enough ideas or sensitive enough instruments, but because the nature of reality places certain truths beyond any possible observation or logical deduction. Recognizing these limits is as important as celebrating what we can discover. The cosmic horizon represents one such limit. Light from galaxies more than about 46 billion light-years away hasn't had time to reach us since the Big Bang, and because space continues expanding, some of this light never will reach us. These distant regions of space are causally disconnected from us. Events there cannot influence us. Information from there cannot arrive here. We could never observe what's happening now in those distant regions, never send a signal there and receive a reply. This horizon is fundamental, not a limitation of our technology, but a consequence of the finite age of the universe and the speed of light. No telescope, no matter how powerful, could see beyond it. Future telescopes might detect fainter objects near the edge of the observable universe, might see galaxies as they appeared closer to the Big Bang, but they cannot extend the horizon itself. The boundary is written into the structure of space-time. Inside black holes, the event horizon creates a different kind of limit. Information from inside cannot escape to the outside, except possibly through the subtle correlations in Hawking radiation that we don't yet fully understand. If you wanted to know what's happening at a black hole's singularity right now, there's no way to find out without crossing the event horizon yourself, and once you cross, you can never report back. The information remains trapped, accessible only to observers who accept permanent exile inside the black hole. Quantum mechanics introduces different limits through the uncertainty principle. You cannot simultaneously know a particle's exact position and exact momentum, not because measurement disturbs the particle, but because these properties don't have simultaneous definite values. You cannot measure a quantum system without changing it, without collapsing its wave function and destroying information about other properties that aren't compatible with what you measured. These aren't technical limitations, but fundamental features of quantum reality. The measurement problem in quantum mechanics might also represent a limit to knowledge. We can calculate probabilities for measurement outcomes using the wave function, can predict statistical patterns over many measurements, but we cannot predict with certainty what any individual measurement will yield. Is this randomness fundamental, truly irreducible, or does some deeper theory exist where outcomes are deterministic and our probability calculations reflect incomplete information? Question of what happened before the Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. The Big Bang is a question of what happened before the Big Bang. Question of what happened before the Big Bang might be meaningless. If time itself began at the Big Bang, then asking what came before is like asking what's north of the North Pole, a question that assumes a framework that doesn't apply. General relativity suggests space-time began at the singularity of the Big Bang, that there was no time before because time is part of the universe, not a container the universe exists within. Quantum gravity might modify this picture, might replace the Big Bang singularity with a bounce from a previous contracting phase or some other structure, but these ideas remain speculative. The multiverse, if it exists in any of its various forms, might be fundamentally unobservable. Other bubble universes from eternal inflation would be causally disconnected from ours, separated not just by distance, but by the structure of space-time itself. Other branches in many worlds quantum mechanics exist, but cannot be accessed from our branch by the very nature of the branching. Mathematical universes corresponding to different mathematical structures would be even more thoroughly separated if they exist at all. These possibilities might be true without us ever being able to prove it. There's also the possibility that our cognitive architecture limits what we can understand. Human brains evolved to navigate the African savanna, to track animals, to read social situations, to manipulate tools. Our intuitions are calibrated for objects moving at everyday speeds. for forces at human scales, for patterns relevant to survival and reproduction. It's remarkable we can understand cosmology and quantum mechanics at all. But there might be aspects of reality too far removed from everyday experience for minds like ours to fully grasp. We work around these limits with mathematics, creating formal descriptions that our intuition can't visualize, but that make consistent predictions we can test. We can work with 11-dimensional spaces in string theory, even though we can't picture them. We can calculate quantum probabilities even though the wave function's meaning remains disputed. We can study black hole singularities mathematically, even though we can't observe them directly. Mathematics extends our reach beyond intuition, but it might not eliminate all limits. Perhaps some questions are not merely unanswered but unanswerable, not because the universe withholds secrets, but because the questions themselves are malformed, asking things that don't have answers the way we imagine. Perhaps reality is fundamentally stranger than any theory can capture, and our models, however successful, are approximations that work within limited domains, but fail to represent some deeper truth. Or perhaps every question can eventually be answered, given enough time. Enough intelligence applied to the problem, enough clever theoretical and experimental work. Perhaps the limits we perceive are temporary, artifacts of our current understanding that future breakthroughs will transcend. We can't know for certain which view is correct, whether knowledge has absolute limits or only practical ones we haven't overcome yet. And that uncertainty itself is a kind of mystery, a meta-question about the nature of questions and answers, truth and reality. Knowledge and its boundaries, there's a peculiar comfort that can be found in accepting uncertainty, in acknowledging that some things remain mysterious, that some questions stay open, that understanding is always incomplete and provisional. This isn't a defeatist attitude, but a realistic one, recognizing that science is a process, not a destination, that each answer generates new questions, that the frontier of knowledge expands rather than closes. Consider how different this is from the certainty that earlier cultures enjoyed, or thought they enjoyed. Ancient cosmologies placed Earth at the center of everything, spheres rotating around us carrying the sun, moon, and planets, the stars fixed on an outermost sphere. Heaven beyond. This picture was wrong, but it was complete, tidy, comprehensible. Every object had its place, every motion its purpose, every question its answer within the framework. Modern cosmology offers no such completeness. We know the universe is vast, probably infinite, certainly far larger than we can observe. We know it's expanding, carrying galaxies away from each other, driven by dark energy we don't understand. We know most of its matter is dark, invisible, detected only through gravity. We know the laws of physics break down at black hole singularities and probably at the Big Bang itself. We know quantum mechanics describes reality probabilistically, that measurements affect what's measured, that observation and reality are entangled in ways we haven't fully unravelled. This knowledge is powerful but incomplete, certain in some aspects but uncertain in others. We can predict how galaxies evolve, but we don't know what dark matter is. We can detect gravitational waves from merging black holes, but we don't know what exists at their singularities. We can measure dark energy's effects precisely, but we don't understand its nature. We can build quantum computers that work, but physicists still debate what quantum mechanics means. Living with this uncertainty requires a certain intellectual humility, an acceptance that current understanding is partial, that future discoveries might overturn ideas we currently take for granted. The history of science is filled with confident theories that later proved wrong or incomplete. Newtonian gravity worked brilliantly for 2 centuries before Einstein showed it was an approximation. Classical mechanics seemed complete before quantum effects were discovered. The steady-state universe looked viable before the cosmic microwave background confirmed the Big Bang. Each generation of scientists has believed they were close to completing physics, to answering all fundamental questions, only to discover new layers of mystery beneath what they thought they understood. In the late 19th century, physicists thought they were nearly done, just a few details to clean up. Then quantum mechanics and relativity revolutionized everything. In the mid-20th century, some thought particle physics was nearing completion. Then quarks and the Standard Model revealed deeper structure. And now we know the Standard Model itself is incomplete, unable to explain dark matter or unify gravity with other forces. This pattern suggests we should be humble about claiming we're close to final answers now. Dark matter, dark energy, quantum gravity. These are likely not the last mysteries, not the final frontier before complete understanding. Solving them will probably reveal new questions we can't currently anticipate, new layers of structure, new phenomena we haven't imagined yet. But this doesn't mean science makes no progress, or that truth is relative and we can't know anything. Our understanding genuinely improves. Newton's gravity was better than what came before, correctly predicting planetary motions and explaining tides. Einstein's gravity is better than Newton's, correctly handling high speeds and strong fields, predicting things Newton's theory couldn't. Some future theory might be better than Einstein's, but it will have to reproduce Einstein's successes in the regimes where relativity has been tested, just as Einstein's theory reproduces Newton's in the weak field. Low-speed regime. Science proceeds by successive approximation, each generation's theories capturing more of reality, working in a wider range of conditions, but probably never reaching absolute final truth about everything. We build models that work within domains, knowing they'll eventually fail outside those domains, hoping each iteration gets us closer to something fundamental, even if we never quite arrive. There's peace in this perspective, in accepting that mystery is not a failure of science, but its fuel, that not knowing everything doesn't mean we know nothing, that uncertainty and knowledge coexist. We can celebrate what we've discovered. The exoplanets and gravitational waves and the Higgs boson, and the cosmic microwave background, while acknowledging what remains mysterious, dark matter and dark energy and consciousness, and how something exists rather than nothing. Perhaps the mysteries are what make the universe interesting, what gives science its sense of adventure and discovery. A completely understood universe might be a boring one. All questions answered, nothing left to explore, no frontier to push toward. The mysteries we've discussed tonight, dark matter and fast radio bursts and black hole singularities and dark energy, and the possibility of other universes, these aren't problems to be solved once and forgotten, but invitations to continued exploration, to building better instruments, to thinking more carefully about what the equations mean, to being surprised by what observation reveals. And as we approach the final section of our journey tonight, perhaps this is the perspective to carry forward, that living with mystery is not just acceptable but enriching, that uncertainty opens space for wonder, that not having all the answers keeps us curious, keeps us looking up at the stars and out at the cosmos with questions still forming, still unresolved, still calling us toward understanding that always remains just beyond our current reach, just at the edge of what we can grasp. Eternally inviting us to reach a little farther. When you truly contemplate the scale of the universe, something shifts in how you see yourself and your concerns. Earth is a small planet orbiting an ordinary star in an unremarkable region of a typical spiral galaxy, one of hundreds of billions of galaxies scattered through observable space, and that observable space might be an infinitesimal fraction of all that exists. We occupy a moment in cosmic time, civilizations rising and falling in the blink of an astronomical eye, our entire recorded history spanning less time than a star takes to complete one orbit around the galactic centre. This perspective could feel diminishing, could make our lives seem meaningless against such immensity. What difference does anything we do make to a universe so vast and old? What significance can human joys and sorrows have in a cosmos that will expand for trillions of years after we're gone, stars burning out, black holes evaporating, entropy inexorably increasing until all complexity dissolves into uniform cold darkness. But there's another way to hold this perspective, one that finds meaning precisely in the contrast between our smallness and our capacity for understanding. We are small, yes, made of the same atoms as rocks and clouds, subject to the same physical laws as stars and planets. Yet we can understand those laws, can trace cosmic history from the Big Bang to the present, can peer across billions of light years and understand what we're seeing, can contemplate our own smallness and find it not diminishing but remarkable. Consciousness is rare in the universe as far as we know. Most of existence is empty space. Quantum fields in their ground states, dark matter streaming through cosmic voids, photons journeying through darkness. Most of the matter that does exist clumps into stars and planets, where temperatures and pressures prevent complex chemistry, or floats in interstellar gas too diffuse and cold for interesting structures to form. Only in narrow windows, on surfaces of planets orbiting stable stars at the right distance, can chemistry become biochemistry, can life arise, can awareness emerge. We might be the only place in the observable universe where matter has organised itself sufficiently to understand itself, to look out at the cosmos and comprehend what it sees. Other civilizations probably exist somewhere in the vastness. Statistical likelihood suggests as much, but we haven't found them yet, haven't detected their signals, remain apparently alone in the small bubble of space we can observe and explore. This rarity makes consciousness precious, not meaningless. The atoms in your body were forged in stellar furnaces, created when massive stars exhausted their fuel and exploded as supernovae, scattering heavy elements into space where they eventually condensed into new stars and planets. You are literally made of stardust. Your substance cycled through cosmic processes spanning billions of years. The iron in your blood, the calcium in your bones, the carbon in your cells, all existed in stars that died before the sun formed. Before Earth existed, before anything resembling life arose, this connection to cosmic processes extends deeper. The particles that make up atoms, protons and neutrons and electrons, formed in the first minutes after the Big Bang, when the universe was a hot, dense plasma cooling and expanding. The quarks and gluons that compose protons and neutrons existed even earlier. In the first microseconds, when temperatures were trillions of degrees, and all the fundamental forces might have been unified in ways we don't fully understand yet. You're not separate from the universe, not an observer standing outside looking in, but a part of it, matter and energy, organised in a particular way for a brief time, connected through ancestry and physical law to everything that exists, temporary but genuine, local but participating in something universal. The same quantum fields that permeate intergalactic space extend through your body. The same fundamental forces govern your chemistry and the nuclear fusion in stars. The same geometry of space-time that curves around black holes curves infinitesimally around you. This cosmic perspective doesn't answer what you should do with your life or how you should treat others or what values you should hold. Science describes what is, not what ought to be, can tell you how stars form but not why you should care, can explain the expansion of the universe but not the meaning you should make of your existence within it. Those questions belong to different domains, to philosophy and ethics and personal reflection, to conversations with yourself and others about what makes life worth living. But the cosmic perspective can inform those conversations, can provide context that might shift how you approach meaning and purpose. Knowing that we're brief patterns in a vast ancient universe might make us more compassionate, more aware that everyone shares this improbable situation of being conscious in a cosmos largely unconscious. Knowing that mysteries remain might make us more humble about claiming absolute certainty, more willing to update beliefs as understanding grows. Knowing that we can understand it all might make us more curious, more eager to learn while we can. The universe doesn't care about us, doesn't arrange itself for our benefit, doesn't punish or reward or take notice. But we can care about the universe, can appreciate its beauty, can wonder at its strangeness, can dedicate ourselves to understanding it better, or simply to experiencing this moment of awareness we've been granted before we return to the cosmic processes we briefly emerged from. Stardust becoming star-aware for a little while, before dissolving back into simpler configurations. The universe briefly contemplating itself through us. There's an aesthetic quality to good physics, a beauty in equations that correctly describe nature, that reveals itself not through flowery language or emotional resonance, but through simplicity, symmetry, the sense that things could not have been otherwise. Physicists speak of elegant solutions, beautiful theories, descriptions that feel right even before they're fully tested, and this aesthetic sense sometimes guides discovery toward truth. Maxwell's equations unifying electricity and magnetism are beautiful in this sense. 4 equations, compact when written in the right mathematical notation, that describe all electromagnetic phenomena, from static electricity to radio waves to light itself. They show how changing electric fields create magnetic fields and vice versa, how electromagnetic waves propagate through space at the speed of light, how the seemingly separate phenomena of electricity, magnetism, and optics are different aspects of one unified electromagnetic field. Einstein's equation E equals mc squared has a similar aesthetic appeal. The simplicity is remarkable, relating energy and mass through the speed of light, implying that mass and energy are interconvertible, that matter contains enormous amounts of energy locked in its very existence. This equation emerged from special relativity's analysis of how objects behave at speeds approaching light, but its implications extended to nuclear physics, to understanding how stars shine through fusion, to atomic bombs and nuclear power, consequences Einstein couldn't have foreseen from the pure theoretical work. General relativity's field equations have beauty of a different sort, more complex than E equals mc squared, but elegantly structured once you understand the mathematics. They relate the curvature of space-time, described by the Einstein tensor, to the distribution of energy and matter, described by the stress-energy tensor. Matter tells space-time how to curve. Curved space-time tells matter how to move. A reciprocal relationship that generates all gravitational phenomena from planetary orbits to black holes to the expansion of the universe. The standard model of particle physics, which describes all known particles and 3 of the 4 fundamental forces, has beauty in its symmetry structure. It's built on mathematical symmetries that dictate how particles interact, how forces work, how conservation laws emerge. The model successfully predicted new particles like the Higgs boson decades before they were discovered, predicted their properties, specified how they should decay, and what signatures they'd leave in detectors, predictions that were confirmed when the technology became available to test them. Yet beauty doesn't guarantee truth. Physicists have been misled by elegant ideas that turned out to be wrong, have pursued beautiful mathematics that didn't correspond to reality, have sometimes privileged aesthetic appeal over empirical evidence. The steady-state universe was elegant, avoiding the messy singularity of the Big Bang. But observations showed the universe did have a beginning. Supersymmetry is mathematically beautiful, predicting a symmetry between matter particles and force particles. But experiments so far haven't found the predicted superpartner particles. The relationship between beauty and truth in physics is subtle. Beauty might be a guide, a hint that you're on the right track, but it's not proof. Ultimately, nature decides what's true through experiment and observation, and nature seems to care nothing for our aesthetic preferences. The universe might be beautiful in its laws, but it's under no obligation to be, and the final arbiter is always what actually happens, not what we'd prefer to happen, or what seems most elegant. There are different types of beauty in physics too. There's the beauty of simplicity, of explaining much with little. like how Newton's law of gravity explained both falling apples and planetary orbits with one equation. There's the beauty of symmetry, of patterns that remain unchanged under transformations, like how physics doesn't change if you rotate your coordinate system or shift it in space or time. There's the beauty of unification, of showing that apparently different phenomena are aspects of something deeper, like electromagnetism unifying electricity and magnetism, or the electroweak theory unifying electromagnetism and the weak nuclear force. Sometimes beauty emerges from what seemed like ugly complications. Quantum mechanics initially appeared messy and counterintuitive. Waves and particles and probability and uncertainty all mixed together in ways that violated classical intuitions. But over decades, physicists found deeper structure, symmetries and principles that make quantum mechanics more comprehensible. Mathematical frameworks like quantum field theory that extend quantum ideas to fields rather than particles, revealing elegant structure beneath the initial confusion. The search for quantum gravity is partly driven by aesthetic motivations, by the sense that having two incompatible fundamental theories, general relativity and quantum mechanics, is ugly, inelegant, incomplete. A final theory should be unified, should show how gravity and quantum effects fit together, should resolve the contradictions and infinities that arise when you try to combine the current theories. Whether such a theory exists, whether it would be beautiful in ways we'd recognise, remains unknown. Perhaps the deepest beauty in physics is the simple fact that mathematical law governs natural phenomena at all, that the universe is comprehensible, that patterns exist to be discovered, that experiments yield consistent, reproducible results we can explain through theory. This didn't have to be true. We might have lived in a chaotic cosmos where no regularities existed, where every event was unique, where understanding was impossible. Instead, we find elegance, find mathematics embedded in nature, find that the universe makes sense in ways our minds can grasp. And perhaps this beauty, this comprehensibility, is reason enough to celebrate what we've discovered and to continue searching for deeper understanding, not because we need practical applications or technological benefits, though those often follow, but because understanding itself has value, because seeing the elegant structure underlying reality brings a particular kind of joy, a satisfaction in knowing that it extends beyond survival or comfort into realms of purely intellectual and aesthetic appreciation that might be unique to conscious beings in an otherwise unconscious cosmos. Wonder isn't just an emotion that happens to us when we encounter something surprising or beautiful. It can be a practice, a deliberate way of engaging with the world, something we cultivate and maintain even when the initial novelty of discovery fades. The mysteries we've explored tonight, dark matter and fast radio bursts and black holes and dark energy and possible multiverses, can become sources of ongoing wonder if we let them. Not just facts to be learned and forgotten, but invitations to keep looking, keep questioning, keep marvelling at how strange existence is. Children have this capacity naturally. Everything is new to them, everything surprising. And they approach the world with endless questions. Why is the sky blue? Where do stars come from? What's at the edge of space? Adults often lose this, not because we know all the answers, but because we stop asking the questions, become habituated to mystery, accept ignorance without curiosity. We know we don't understand quantum mechanics or consciousness or why there's something rather than nothing, but we don't think about it much. Don't let the mystery touch us. Cultivating wonder means staying connected to that childlike curiosity while adding adult understanding, knowing enough about physics and cosmology and mathematics to ask questions precisely, to appreciate when answers exist and when they don't, to distinguish real mysteries from merely complicated phenomena we could understand with more study. It means seeking out the things that make you stop and think, that shift your perspective, that remind you how extraordinary ordinary existence is. The night sky offers a readily accessible source of wonder if you take time to engage with it. Those points of light aren't just decorative. They're other suns, many of them larger and brighter than our own. They're like travelling years or centuries or millennia to reach your eyes. The Milky Way's band across dark skies isn't clouds or mist, but billions of stars. Our galaxy seen edge on from our position within it. The fuzzy patches that aren't stars are other galaxies, island universes like our own, visible despite being millions of light years away. Knowing this transforms observation. It's not just light you're seeing, but information, photons that left those stars when Earth was different, when your ancestors were different creatures or hadn't evolved yet. Photons that travelled unimaginable distances to enter your eye at this particular moment. You're connected to those distant suns through this exchange of photons, participating in a kind of cosmic conversation where they speak in light and you listen by seeing. Wonder can also be found in the small, in the quantum weirdness underlying everyday experience. The solidity of the floor beneath you is an illusion in a sense. Atoms are mostly empty space, and the electromagnetic repulsion between electron clouds is what prevents your feet from passing through. The chemical bonds in your body are quantum mechanical, electrons in superposition spanning molecular orbitals, their wave functions overlapping in ways classical physics never predicted. Radioactive decay, which happens constantly in trace radioactive atoms in your body and environment, is genuinely random, irreducibly so, not determined by any prior cause we can access even in principle. Each decay event is a quantum measurement, a collapse of the wave function, reality choosing one possibility from many each time an unstable nucleus breaks apart. You're embedded in quantum processes, not separate from them, your very existence depending on chemistry that wouldn't work without quantum effects. The history in everyday objects can evoke wonder too if you think about it. The water you drink contains molecules that cycle through countless organisms, fell as rain in ancient storms, flowed in rivers that carved valleys, pooled in oceans where life first arose. Some water molecules in your body might have been in dinosaurs, in the first forests, in comets that bombarded early Earth. The oxygen you breathe was produced by photosynthesis, plants and algae splitting water molecules and releasing oxygen, a waste product to them but essential to us. Wonder doesn't require exotic phenomena or cosmic scales. It can be found in examining anything closely enough, in asking how it works, where it came from, what principles govern it. Why do ice crystals form in the patterns they do? How does your brain create the experience of seeing colours? What determines whether a raindrop will freeze or remain liquid at temperatures near freezing? Every question leads to others, to deeper understanding that generates new questions, to a kind of infinite regress where wonder feeds on itself, each answer revealing new mysteries. But wonder can also be quiet, contemplative rather than excited. It's not always gasping amazement at spectacular phenomena, but a steady appreciation for existence, a maintained awareness that being here at all is improbable and temporary and strange. The universe spent billions of years getting to this point, stars forming and dying, heavy elements accumulating, planets coalescing, chemistry complexifying, life arising and evolving, consciousness emerging. Your ancestors survived long enough to reproduce, every single one in an unbroken chain stretching back to the first self-replicating molecules. You exist now, briefly, aware of existing, able to contemplate your own improbability. This quieter wonder supports the energetic kind, provides a foundation of appreciation that keeps curiosity alive when novelty fades. It's what makes people become scientists, what sustains them through years of difficult work on problems that might not be solved in their lifetimes, what drives the construction of ever more sophisticated instruments to probe ever more subtle phenomena. The universe didn't have to be interesting, didn't have to contain mysteries worth solving, but it does, and wonder is the appropriate response. The stance that honours the strangeness of existence while motivating efforts to understand it better. Human lives are short, 70 years if fortunate, perhaps fourscore with modern medicine, a century at the outside for the oldest among us. Our civilizations are brief too in cosmic terms, a few thousand years of written history, 10,000 since agriculture began, perhaps 50,000 since behaviourally modern humans appeared. All of recorded history. Everything that's happened since writing was invented occupies less time than a single heartbeat on cosmic timescales. The universe is 13.8 billion years old, nearly 14,000 million years, a span of time that becomes meaningless if you try to comprehend it directly. Better to build up through intermediate scales, feeling your way toward the vastness. Earth formed 4.5 billion years ago, about a third of the universe's current age. Life arose perhaps 4 billion years ago, simple cells that left no fossils known only through chemical traces. Photosynthetic organisms began releasing oxygen maybe 3 billion years ago, gradually transforming Earth's atmosphere from reducing to oxidizing over hundreds of millions of years. Multicellular life arose less than 1 billion years ago. Dinosaurs went extinct 66 million years ago, recent in geological terms. Humans and chimpanzees shared a common ancestor about 6 million years ago. Homo sapiens, as an anatomically distinct species, has existed for perhaps 300,000 years, a blink. Agriculture is 10,000 years old. The pyramids of Egypt, ancient to us, are only about 4,500 years old, built within the last 1% of Earth's history. On cosmic timescales, all of human civilization happens in an instant. All of complex life on Earth occupies just the last fifth of planetary history, and Earth itself formed a third of the way through cosmic time. Most of the universe's history happened before our planet existed. Stars forming and dying in cycles that processed hydrogen into heavier elements, galaxies assembling and merging, the cosmic web taking shape, all preparing the stage for solar systems like ours to eventually condense. Looking forward, the future timescales become even more extreme. The sun will continue burning for about 5 billion more years before exhausting its hydrogen and expanding into a red giant, engulfing Mercury and Venus, possibly Earth too. Even if life survives on our planet or spreads to others, the sun's eventual death is certain. But 5 billion years is plenty of time for evolution to produce forms of life we can't imagine, for civilizations to rise and fall countless times, for intelligence to spread through the galaxy if it chooses to, for transformations we can't predict because we're too early, too limited in vision. The galaxy will continue for trillions of years, stars forming from remaining gas, though the rate of formation will decline as gas is consumed or ejected. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, the two spirals merging over hundreds of millions of years into a single elliptical galaxy. Individual stars will rarely collide. They're too far apart, but the galaxy's structures will be completely reorganized. New bursts of star formation triggered where gas clouds slam together, the central black holes eventually merging in a tremendous release of gravitational waves. After star formation ends in perhaps 1 trillion years, existing stars will slowly burn out, the longest-lived red dwarfs finally exhausting their fuel, galaxies becoming graveyards of white dwarfs, neutron stars and black holes, dark except for occasional flashes when stellar remnants collide or matter falls into black holes. But 1 trillion years is so far in the future that making detailed predictions becomes impossible. We can't know what intelligence might accomplish given such vast spans of time, can't predict what currently unknown physics might become relevant, can't anticipate what forms existence might take. Even after stars go dark, black holes remain, patient and cold, slowly evaporating through Hawking radiation over timescales that dwarf all previous cosmic history. A solar mass black hole takes 10 to the power of 67 years to evaporate. Superstring theoretical objects that make all previous time seem instantaneous by comparison. After they evaporate, the universe contains only the most stable particles spread through ever-expanding space. approaching but never quite reaching absolute cold and complete uniformity. These future timescales make individual human concerns seem almost absurdly small. What does it matter what you accomplish or fail to accomplish when all of it will be erased long before the universe reaches its cold finale? What significance can any human endeavour have against such vast stretches of time? If everything ends in heat death regardless, why does anything matter? But perhaps the question is backwards. Perhaps meaning doesn't require permanence. Perhaps what makes life valuable is precisely its brevity, its improbability, its temporary flourishing against the background of cosmic processes that don't care. Flowers aren't less beautiful because they wilt. Music isn't less moving because it ends. The fact that human civilization will eventually vanish doesn't diminish the reality of joy or love or discovery experienced now, in this brief window of cosmic time when matter has organized itself into forms capable of experiencing anything at all. The long view reminds us to hold our achievements lightly, to avoid taking ourselves too seriously, to accept that we're temporary participants in something vast and ancient that will continue long after we're gone. But it doesn't require nihilism or despair. It can instead ground a kind of humility and gratitude, an appreciation for the improbable gift of existence, a resolve to make these brief moments meaningful in whatever way feels authentic, not because the cosmos will remember, but because consciousness now, awareness experiencing itself, has intrinsic value independent of duration or cosmic significance. Some mysteries resist solution not because they're scientifically difficult, but because they might not have scientific answers at all. Questions that push beyond what physics can address, that reach into philosophy or simply accept boundaries where inquiry must end. These quietest mysteries sit beneath the ones we've explored, more fundamental than dark matter or quantum gravity, more personal than cosmic expansion or black hole evaporates. Why does anything exist at all? Not just why does this particular universe with these specific laws exist, but why is there something rather than nothing? Nothing seems simpler than something, seems like it should be the default state, yet here we are. In a cosmos filled with galaxies and stars and planets and life and consciousness, the question might be unanswerable in principle, might be asking something malformed, but it sits there quietly, refusing to dissolve. Science traces causes back through time, explains this in terms of that. But every explanation assumes something already existing that does the explaining. The Big Bang happened because quantum fields existed in a particular state. But why did quantum fields exist? Why did the laws governing them take the form they did? You can push back further, propose multiverse theories where different laws apply in different universes, but the multiverse itself requires explanation, rules determining how universes form, how physical laws are selected. Eventually you reach something you can't explain, some brute fact you must accept without deeper justification. Perhaps existence is simply a brute fact, something that is without reason or cause, the foundation everything else builds on but which has no foundation of its own. Perhaps asking why existence exists is like asking what north of the North Pole is, a question that seems meaningful but actually isn't, that assumes a framework that doesn't apply. Or perhaps there is an answer we can't grasp with human minds, a deeper principle or necessity that makes existence inevitable rather than contingent, but one too far beyond our conceptual architecture to comprehend. Consciousness presents similar mysteries that blend the scientific and philosophical. We know conscious experience emerges from brain activity, that neurons firing in patterns generate the subjective sensation of being someone, somewhere, experiencing something. We can map which brain regions activate during different experiences, can alter consciousness with drugs or meditation or electrical stimulation, can even predict some aspects of what someone is conscious of by analysing their brain activity. But knowing the neural correlates of consciousness doesn't explain what consciousness is, doesn't answer why physical processes in a brain generate subjective experience at all. Why does it feel like something to be you? Why is there an inner perspective, a sense of I, an experiential quality to existence? Philosophers call this the hard problem of consciousness, distinguishing it from easier problems of explaining behaviour or information processing, which are difficult but tractable in principle. Consciousness might be fundamental, as basic as mass or charge. Something physical systems have to varying degrees depending on their structure and organisation, or it might emerge from complexity, appear when information processing reaches a certain threshold or takes on particular patterns. Or perhaps our understanding of matter is incomplete, missing something essential that would make consciousness comprehensible rather than mysterious. We don't know, and the question sits there, quiet and persistent. Then there's the question of meaning and value. Science describes what is, maps cause and effect, explains mechanisms and patterns. But it can't tell you what you should value, what makes life worth living, whether anything objectively matters. These questions belong to different domains, to ethics and aesthetics and personal philosophy, to conversations about what it means to be human that science can inform but not resolve. The universe as described by physics is indifferent, operating according to mathematical law without purpose or goal, without caring about outcomes, without judging good from bad except in terms of energy gradients and entropy. Stars don't shine for a reason. They shine because nuclear fusion releases energy, and lighter nuclei fuse into heavier ones when conditions allow. Life doesn't exist for a purpose. It exists because chemistry can create self-replicating patterns under certain conditions, and those patterns persist through reproduction. Yet we experience meaning, value things, make choices based on what we care about, create art and music and stories that move us, form relationships that matter profoundly. This meaning isn't out there in the universe to be discovered like a new particle or a distant galaxy. It's something we create or participate in, something that emerges from being the kind of conscious social beings we are, something real in its effects, even if it has no foundation in fundamental physics. Perhaps this is okay, perhaps meaning doesn't need cosmic grounding to be valid. Perhaps it's enough that we experience it, that love feels important even if physics doesn't acknowledge importance, that beauty moves us even if beauty doesn't appear in equations, that curiosity drives us even if the universe doesn't care what we discover. The absence of objective cosmic meaning doesn't make subjective human meaning false or worthless, just differently grounded. Rooted in our nature rather than in nature's laws. The quietest mysteries are the ones we live with daily without usually noticing. The strangeness of being conscious at all, of caring about anything, of experiencing the world as meaningful despite knowing about cosmic indifference, of finding joy and beauty in a universe that will eventually fade to cold darkness regardless of what we do. These aren't problems to solve, but conditions to accept. Boundaries of understanding where science gives way to philosophy, and philosophy gives way to simple acknowledgement that some things just are, without deeper explanation, present as the context within which all our questioning happens. And perhaps these mysteries are what make the cosmic mysteries worth exploring, what connects our brief human concerns to vast astronomical scales, what makes us care about dark matter and black holes and the fate of the universe. We're embedded in this cosmos, made of its substance, governed by its laws, but also aware of it, capable of wondering about it, able to find meaning in understanding even small pieces of how it works. The connection between the personal and the cosmic, between consciousness and cosmos, between meaning and matter, remains mysterious. But it's our mystery, the one we experience directly, the foundation of everything else we think about or care about or discover. We've travelled together for 2.5 hours now, drifting through cosmic mysteries from the invisible dark matter shaping galaxies to the flashing signals from deep space, from black holes where time and space exchange their roles to the accelerating expansion driven by dark energy, from possible multiverses beyond observation to the quiet questions that sit beneath all the scientific ones. questions about existence and consciousness, and meaning that physics can inform but perhaps never completely answer. From dark matter's gravitational fingerprints across the cosmic web to fast radio bursts flashing from distant galaxies in milliseconds, from black hole singularities where our physics breaks down to the dark energy pushing space apart, from the humans doing patient scientific work to the instruments extending our senses, from the mathematics describing reality to the wonder we can cultivate in contemplating it all, from cosmic timescales stretching to heat death and beyond, to the immediate experience of being conscious now, we've explored mysteries at every scale, from quantum to cosmic, from observational to philosophical. The answer, as honestly as I can give it, is that the universe remains mysterious in profound ways, that we've learned tremendously much over the past century of modern cosmology and physics, enough to transform our understanding from ancient cosmologies to precise models of cosmic evolution, from simple atoms to quantum fields and curved space-time, yet enough mystery remains to fuel centuries more of exploration. What we've learned suggests that learning... Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. What we've learned suggests that learning more is possible, that mysteries can be solved or at least refined into more precise questions, that understanding genuinely progresses even if it never reaches completion. Perhaps the answer is that mystery is not failure but opportunity, that the unknown is not absence but presence, the presence of something yet to be discovered, something waiting for the right observation or the right theoretical insight or the right experiment to reveal itself. Dark matter might be detected tomorrow or might require new physics we haven't imagined yet. Fast radio bursts might be understood once we observe enough of them, or might reveal phenomena we don't currently have framework to comprehend. Quantum gravity might emerge from string theory or loop quantum gravity, or something entirely different that the next Einstein will envision. If you enjoyed this slow drift through cosmic mysteries, a like and subscribe helps reach others seeking the same peaceful way to end their day. To fall asleep learning about the universe's wonders without fear or urgency. To let consciousness fade while contemplating mysteries larger than ourselves. Leave a comment sharing where in the world you're watching from, what mysteries speak most strongly to you, what questions you carry about the cosmos and our place within it. And to those already subscribed, thank you for being here, for joining these journeys night after night, for trusting these explorations to accompany you towards sleep. Wherever you are in the world, whatever time it is for you right now, I hope you're comfortable. I hope your breathing has slowed and deepened naturally as we've talked. I hope your thoughts have quieted somewhat, the urgent concerns of the day fading in importance as cosmic perspectives settle over them like gentle snow. I hope your body feels heavy and warm, relaxed into whatever surface supports it, ready for the transition from waking to sleeping that comes to all of us eventually each day. Look up at the stars if you can, if there are stars visible where you are. Or imagine them if you can't, points of light scattered across darkness, each one a sun like ours, many with planets, perhaps some with life, perhaps some with consciousness looking back toward us across the light years, wondering as we wonder about what else exists out there in the cosmic dark. All those photons travelling through space, some for centuries or millennia, converging on your eyes at this particular moment in cosmic time, connecting you to distant suns through this exchange of light. And beyond the visible stars, galaxies by the hundreds of billions, Island universes like our own Milky Way, each containing hundreds of billions of stars, spread through space so vast that light takes billions of years to cross it. All of it expanding, all of it evolving. Dark matter halos holding galaxies together, dark energy pushing them apart, fast radio bursts flashing in the depths, black holes waiting patient and strange at galactic centres, all of it real, all of it vast. All of it operating according to mathematical laws we're slowly learning to read, slowly learning to understand. You exist within all this, briefly, improbably, a local complexity in a universe trending toward uniformity, a temporary pattern of matter and energy that can know itself, can wonder about itself, can contemplate mysteries and seek understanding, can experience the quiet joy of learning how things work or the peaceful acceptance of not knowing everything. Your consciousness is rare and precious. Your awareness a gift the universe has given itself through the particular organization of atoms that is you. Sleep well tonight. Dream of stars if you dream at all, of galaxies spinning through darkness, of mysteries solved and mysteries remaining, of the patient work of understanding, of the beauty in equations and observations, of the wonder that existence generates when it becomes aware of itself. Dream of telescopes scanning the sky, of particles streaming through underground detectors, of mathematics describing reality, of humans looking up and asking why. Know that the mysteries will be there tomorrow, waiting patiently for new insights, new observations, new theories that might explain them or reveal new depths we hadn't imagined. Know that the universe continues whether we understand it or not. Stars burning, black holes evaporating, space expanding, galaxies evolving, all according to laws that care nothing for our comprehension, yet are comprehensible anyway, offering themselves to minds curious enough to look carefully, to think clearly, to accept uncertainty while pursuing understanding. Rest now. Let it all go. The questions will keep. The stars will shine. Space will expand. Time will flow. And you, briefly, beautifully, improbably, get to be here, aware of it all, participant in the universe's long story of matter becoming conscious, if only for a little while. Good night.